Let's look at this problem. Calculate the line integral, and you are given the equation there, along one revolution of the helical line specified parametrically as, and you are given the equation for x, y, and z. Okay, so let's first write down what we are being asked. So we are asked to calculate this integral where L is the curve given by r of phi. So clearly our parameter must be phi because we have phi everywhere, yeah. So this r of phi is equal to a function x of phi, y of phi, and z of phi, which is given by r cosine phi, r sine phi, and b times phi. And this curve actually corresponds to a helix, which I could draw. So it corresponds to a helix, which is rising. Yeah. So if you imagine you have a cylinder and we are just moving up throughout the wall of the cylinder in this helix shape. So that's our L curve, this red line there. Okay, so what does this mean? As I said in the previous video, don't be confused if you ever get asked a question in this format. It just means this. So this is the x component of f, this is the y component of f, and this is the z component of f. Okay? So basically all that is being asked is to calculate, is another way of asking to calculate f dot dr with f being given by the vector. This will be the x component, so it will be x. This will be the y component, it will be minus y. And this will be the z component, which will be z. Okay, so that's all that this question is asking. So let's follow the steps that we know for calculating this. So 1, we parameterize the curve. Fortunately, that has already been done for you. Okay, so we already have that. And we know that the parameter runs between 0 and 2 pi because the question asks for one revolution of the helical line. Okay, so only one revolution. Great. Second, we have to calculate dr, the vector differential displacement. So let's do it with the definition. So dr vector is equal to the derivative of the parameterized curve with respect to the parameter times the differential of the parameter. So I have to do the derivative of this with respect to phi. So I get minus r sine phi, r cosine phi, and then I get here b d phi. Okay, so this will be the dr vector. Notice that we could decide to write this as minus r sine phi d phi, r cosine phi d phi, and b d phi. And this would be equivalent to writing dx, dy, and dz. Okay, so for example, x was a function of phi, right? Because, okay, so x is a function of phi, which is r cosine phi. So dx is just the differential of that function, so it's just minus r sine phi d phi. Okay, so everything fits like in a puzzle. So now this means that we are ready to calculate the integrand. Evaluate the integrand at the surface. Sorry, at the surface, not at the curve. So we have to evaluate f dot dr, which we could either we write f and dr like this, and we do the dot product, or we just evaluate this, substituting x, y, and z, and also substituting dx, dy, dz, right? We can do it both ways, they will be the same thing. So let's do it in the usual way. So this is f dot dr, which is over here, times d phi. So now we need to do the dot product, but also not only do we have to do the dot product, but we have to substitute x, y, and z for the values that x, y, and z have on our curve. So we need to substitute x equals this, y equals this, and z equals this from the parameterization of the curve. Okay? So substitute x, y, and z as a function of phi from the curve. So we do that substitution. So we have x equals r cosine phi. Then we have minus y, which will be minus r sine phi. And then we have z, which will be b phi. This dot product with this. And b times d phi. And now we have to do the dot product, yeah? Remember, this is a dot product between two vectors and we need to evaluate it. So we will have to do this times this, plus this times this, plus this times this. So it will be minus r squared cosine phi sine phi minus r squared sine phi cosine phi plus b squared phi, and all of that multiplied by d phi. These two terms are the same, so it becomes minus 2r squared cosine phi sine phi plus b squared phi d phi. Okay, so that is now our integrand, which we can see just as a function. So the sanity check that I always recommend at the end of step 3 is, whenever you have the integrand, is it a function of phi only plus constants? And indeed you have phi's, you have r, which is a constant, and you have b, which is also a constant, which determines the pitch of the helix. Okay, so yes, this is ready for integration. So step 4 will be to integrate this. So we can do the calculation of the integral from of this. So we are integrating over our parameter phi, and the limits of our parameter phi are from 0 to 2 pi. So we have to perform this single integral. If you're scared about this integral, you shouldn't, because actually the result is quite simple. So let's leave minus 2r squared outside. Okay, so let's do the integral from 0 to 2 pi of cosine times sine, and then plus b squared times the integral from 0 to 2 pi of phi d phi. So, oops, don't forget your d phi's. Okay. So how do we do this integral? So when you have a cosine multiplied by a sine, the answer is actually very easy. If you just think about it carefully, it's just 1/2 of sine squared phi. Okay, why is that? Because if you see this and you want to make the derivative of this, you have a sine squared, so you bring the 2 down, so this cancels out with the 1/2. Then you multiply by the derivative of what's inside the square, which is the derivative of sine, which is the cosine, and then you multiply by the parenthesis to the power the power that it was minus 1. So 2 minus 1 is 1. Yeah. So remember, if I write this like this, it's even clearer. Yeah. So when you do the derivative of a parenthesis to the power 2, you bring the 2 down, then you multiply by the derivative of the parenthesis, and then you multiply by the parenthesis but subtracting 1 to the exponent. Okay, so you end up with cosine times sine, evaluated between 0 and 2 pi. And then plus b squared times pi squared over 2, evaluated between 0 and 2 pi. Okay, so the answer to this is 0 because the sine of 2 pi and the sine of 0 are both 0. So we are only left with this term here, which will be 4 pi squared divided by 2, that's 2 pi squared b. And that finalizes, sorry, b squared. And that finalizes our calculation. Okay? I hope that was clear. Thanks for watching. See you in the next video.